Hello, everybody. Thanks for coming today. So we have a few people on the line today, and we have the great pleasure to host Corentin for this week and next week, where we'll be having the Juno Magnetosphere Working Group, where he's going to be giving a seminar also there. So he's visiting us from Dublin, the Dublin Institute of Advanced Science. So his research team focused on the study of interaction taking place in the magnetosphere and the auroral phenomena that results from it. He did his PhD that was entitled Jovian Auroral Radio Emission, Remote and In situ Observation and Simulation at the Paris Observatory, working with data from Voyager, Cassini, Wind, Juno, and the Nançay decameter array, which I believe he's going to talk a little bit more about today. And then he worked at IRAP in Toulouse to perfect his knowledge on the radio emission and the theory of the associated mechanisms, such as the growth rate of the radio emission and the saturation. And then he went to Toulouse to learn how to use the data from the in situ particle JADE on Juno. And now he's
the HBA antenna and the low frequency, so high frequency band antenna and low frequency band antenna. And this site of Nançay has been hosted radio instruments since a while. For example, you have the Nançay decameter array data, which is able to look at the Sun and Jupiter mostly since the 80s, so 40 years ago. And so there is a huge knowledge about the radio instruments on that Nançay site. So what is LOFAR? I'm sure you already know, but LOFAR is an international telescope with a lot of antenna. The core of the instrument being on the Netherlands with the Dutch station. We have an example here, and you have something like 13 stations in all Europe. So in Ireland, for example, at Birkastel, which is called Irish LOFAR telescope. You have some in the UK, in France, a lot in Germany. You also have one in Italy, which is not in this picture. You have some in Poland, in Sweden, etc. So we went from LOFAR with the station here to NENUFAR. So you can see that there is a lot more antenna, and so we took the low frequency band and the high frequency band antenna to produce this kind of antenna, which are really looking like the LWA antenna actually. And so this allows us to cover most of the radio emission that can be observed by the LOFAR station, and we can also see a bit higher in frequency. This is, NENUFAR is a sensitive, large, compact, very low frequency array. It can look large field of view, multi-beam, sensitivity to extended structure. It's a complement to LOFAR, the high resolution in the low frequency band antenna with more sensitive baselines. And well, it's developed by the French low frequency radio community. So NENUFAR. So NENUFAR is built with, you had a lot of antennas. So each antenna is gathered by 19 antennas in what we call mini arrays. And with at NENUFAR, you had 96 mini arrays that are composed of 19 antennas, which is almost 2,000 antennas in total. And you can do a lot of things with that. You can be a LOFAR backend for the HBA, LBA instruments, and you can be in a LOFAR superstation too. I will come back in that later. You can use NENUFAR as an imager, and you can use NENUFAR as beamformer to do dynamic spectrum, for example. The antenna are aligned at 45 degrees from the meridian, so northeast direction to southwest direction and northwest to southeast. So the combination of these two linear polarized signals allow us to have the full polarization, the 4 Stokes parameters, which can give us the full polarization of the signal we are observing. So the distribution of mini arrays, so you can see that each point here, you can see here, is, well, 19 antennas. And so right now in operation, you have 90 core and mini arrays, and you have 4 remote mini arrays at a few 1 or 2 kilometers, here, and 1 here. And it's still to be built 16 core mini arrays and 2 remote mini arrays. That's the sensitivity. So that's the core. That's the 4 distant mini arrays that are built. One will be built here, and one here still need to be built. So these really far mini arrays are used to increase the baseline to be able to increase the resolution that you can have with this distant mini array. Sorry. Yeah, that's some example of what we can observe, the antenna position, but yeah, I will skip that, but this is some observation that we can do with that first few examples. So the sensitivity of this antenna, so you have here you have an antenna here, and on top you have a pre-amplifier that gives you more signal, and just an example of, so in purple or pink, it's the LOFAR sensitivity. And in black is the NENUFAR sensitivity. So you can see that at low frequency, so 10 to 30, 20 megahertz, we have the same spikes here, which are due to the ionosphere that perturbs the signals. And at higher frequency, you can see that the resolution of the sensitivity of NENUFAR is higher than LOFAR, which is really interesting to look at, for example, Jupiter observation or the observation coming from the sun. So yeah, that's the disposition of antenna. It's not as for LOFAR randomly spaced. The difference here on the distance between each antenna was really studied to be able to have the better pointing using all these mini arrays. Okay, so that's a really busy plot, so don't read everything. That's not the purpose. It's just to show you a bit the path of the signal from the antenna to the preamplifier to some of the different modes we have. So there is mainly 3 different modes. One which is connected to LOFAR, so the LOFAR station in France or the LOFAR superstation, so all the stations. This is to do some beamform, and this is to do some image with NENUFAR. So let's start with the connection to LOFAR, because that will be the quicker to explain, because it's not done yet, it's in progress. So we are able to connect, so the idea is to use NENUFAR to do some interferometry with the other stations, or all the stations at once. This is still in progress, because to discuss with all these other LOFAR stations, it demands to have more knowledge on that, and so it needs to be tested before be able to do that, so this is in progress. So the beamformer, so it's called the backend is called LANUBA for LOFAR-like advanced new backend. It allows us to do some dynamic spectra. It is used for SETI. It is used for the imager also too, because it's connected. And so what we can do with that, for example, is this kind of not image, well, it's images, but dynamic spectra, so you have the time here and the frequency, and we are using that, for example, here, it's a Jupiter example. So we are observing the signal coming from the interaction between Io and Jupiter here, and we can do some really high resolution. So what you are seeing here, the label are missing, but it's 1 second here, 1 second of data. So that, and we can go down to a few milliseconds of data, so that allows us to, well, look at the microstructures of this kind of emission. And then the third mode is to do some, it's a NENUFAR imager, to do some, well, images. And so here I think you have an example, of the first light of the radio telescope. This is an observation of Virgo A, and you can see the movie here, and you can see, well, images made from the core of NENUFAR. So that was the first light of the telescope. So to be more user-friendly, because the telescope is now open to the community and everybody can propose some observation, and so you can have access to this website, which is called the Virtual Control Room, and there's a lot happening here, but you have the real time, you can look at what's happening in real time, you can look at the maintenance, you can look at the maps, you can look at the programs, you can ask for suggestion for if you want to make some observation, etc. So if you want to have access to that, I will come back on that later, but you need to send an email to the head of the radio telescope. On that website, you can look at the NENUFAR TV, which is what is happening currently. So if you want to look at what we are observing right now, you can go to this web page, and you should be able to see. So this is, for example, the position of the mini array, so the gathering of 19 antennas, and you can see which one are used, and you can see which one are seeing what, and then you can look at the beam, what the beam is seeing, and what's happening at the zenith. Oops. So because a new telescope was built, it was needed to develop new tools, programming tools, to be able to look at the data, because the size of the data is huge. I don't remember exactly the size, but it's really huge. So it was needed to develop some new process pipeline. And so it was done, so there were already some IDL pipeline that were used for LOFAR, and so Alan Lowe developed this pipeline in NENUFAR, in a Python, which is called NENUPy, for NENUFAR Python, as you can imagine. And so you have a nice documentation if you want at that. And so if you want at some point to use the data that were already taken, you can go to this web page and you will have all the explanations to use the NENUPy package to be able to read and play with the data and process the data. And so really quickly, you have some routine to do some data manipulation. You have some routine to look at the property of the NENUFAR, the sensitivity, the pointing during the observation. You can look at the ephemeris, you can do some simulations, and you can look at and you can also program the scheduling of some observation if you want to propose some observation you want to do. So okay, that was the technical part of NENUFAR, the antennas, etc. So now, what kind of science can we do with NENUFAR using all these tools and all these antennas? So at the beginning, the science with NENUFAR was split into 17K projects. So from cosmic dawn to the observation of the sun, to SETIs, joint Jupiter studies, planetary lights, etc. And so from the early science phase, so from July 2019 to December 2022, so almost, so well, still in October, but it was planned to have 8,000 hours of observation, split it between all the KP to test what we can do and what we can achieve with this observation. And since this summer, so, well, actually the first call is now closed, but the next one will be open in January or March, every 6 months. And so since this summer, it's open. There were open calls for everyone to propose some observation, depending on one of these KP if you like, but it could also be whatever observation you want. So because it's a NENUFAR, it's a station that should be connected to LOFAR. There is probably 1/3 of the time which is deserved to observe in connection with LOFAR, and the other 60% for the NENUFAR observation to this KP. So now let's look at some recent results. So I will go quickly on most of them because I'm not an expert about all this stuff like cosmic dawn, but here it's an observation of the cosmic dawn. So they were observing the North Celestial Pole. They were aiming to detect the 21st centimeter signal from the cosmic dawn at some specific megahertz. And so at the beginning, they were looking at some sky model to see what they were supposed to see, and in second phase, they were observing. And so here you have the first images that they were able to do. So it's a different field of view, to 45 degrees down to 21 degrees, and they were observing at different frequencies, and this is the Stokes I parameter, so the intensity. We can also observe pulsars. So there were a pulsar survey with NENUFAR. The idea was for this first paper, and the thesis of Louis Bondeneau, it was to look at what we can detect with NENUFAR if we were able to detect already known pulsars, to then be able to detect new pulsars. And so the main results of, I think, of this thesis was to be able to have a nice pipeline process to detect the pulsar, and he was able to detect pulsars already now with a better sensitivity. And so now they are looking at they are programming a lot of observation to detect new pulsars. They're also looking at the cluster filament and cosmic magnetism. And so here you can see some magnetism. Well, I'm not sure exactly of what it is here, but maybe some of you know about that. But this is the cosmic filaments and magnetic pilot survey, and this is the COMA cluster. It was published by, I think it's now published. It's not anymore on archive. It's published on at APG, I think. We can also look at fast radio bursts, and so there is no results on that. The idea was to first have a pre-processing pipeline which was operational. So the idea was to look at some signal that we can observe without any fast radio burst in it, add a random fast radio burst that you can see here, and then with the pipeline, look at if we were able with the pipeline to detect it with a nice signal-to-noise ratio, which was the case here. So you have noise, then you add like a dummy fast radio burst, and you are able to detect it with the pipeline. And they are now in the process of doing the same. So that's another example. And they are now trying to do the same, and so I think that's the first observation, and they were able to detect this fast radio burst in real image, in real observation, with the pipeline that I was presenting just before. There is also one KP looking at the sun. So here you have an example of an observation made with NENUFAR. You have type 2 bursts here, type 2, so three different type 2 bursts. And in that study, they were able, by looking at this, to reconstruct the position of the sources of this type 2. We can also look at Jupiter, as I was saying before. So for example, in this study, they were looking at this emission you can see here, which are related to the interaction between Io and Jupiter. You have a current connecting both, and because you have accelerated electrons, at some point you have instabilities that can produce radio emission. And so they were, in that study, looking at this signal from different point of view, from NENUFAR, from Juno, and from also HST in UV. And using all this observation, they were able to reconstruct and to determine some parameter of the emission, some characteristics of the emission, like the beaming of the emission and the energy of the electrons involved in this emission. And so currently they are doing the same. That was like a first test on it, and they are doing that with all the Nançay decametric array observation, which is 40 years of data, which means, well, a lot of observations and signals. So this first example was with the low resolution mode of NENUFAR, and this is with the beamform observation. So it means that we can go down to 1 second. So this is an LOFAR observation, but we can do the same with NENUFAR. And so we can clearly see that there are a lot of substructures in this IO-induced radio emission. And so if we are looking at the really high resolution, we can see that we are observing some bursts of this emission, and these bursts are directly linked to the movement of gyration of the electrons along the magnetic field lines. And by looking at the slopes of these bursts, we are able to determine the energy of the electrons, and we can also look at if we are observing some acceleration process if the burst, if the slope of the burst is brutally changing. And of course, with NENUFAR, the idea is to be able to be connected to all the LOFAR stations, and so to do some interferometry. And so by doing interferometry, we should be able to do some images and to put constraints on the location, the exact location of the sources. So one of the really important topics for Philippe Zarka, who built this radio telescope, is to look at exoplanets and star interactions. So the idea is to be able to detect the radio emission coming from the interaction between a star and an exoplanet, which is the kind of the same process that makes radio emission from Io and Jupiter. And so the idea is to be able to look at that. And so since a few decades, people are claiming to not detect, but put some constraint on how we should detect the radio emission. And actually, with NENUFAR, we are now at the and we have enough sensitivity to be able to detect this emission. And so there is a lot of observations that are conducted. Yeah, that's okay. And so looking at what we have in terms of interaction between a star and a planet, or a planet and satellite like Jupiter and Io, we have determined that for one exoplanet known, the V711 we should be able to observe a radio power of this value, and the sensitivity of NENUFAR should be enough right now to observe this radio emission coming from this exoplanet star interaction. And so right now, the pipeline to pre-process the data is operational, and so we are hoping that now we are conducting some observation. We have a lot of hours of observation. Well, we are hoping that we will detect a signal of an exoplanet, a radio signal coming from an exoplanet, which is really interesting because these kind of radio emissions are directly linked to the amplitude of the magnetic field line. So it means that if you are able to detect a radio emission coming from a star-exoplanet interaction, you will have direct information on the presence of a magnetic field, and we should be able, with some simulation after that, to put some constraint on the magnetic field on an exoplanet. Yeah, it's a hot Jupiter, yeah. But we are also right now doing some simulation to look at, for example, Proxima Centauri b, which is a brown dwarf, I think, the star, and the planet is like a super Earth planet. And so we have some constraint on the orbits of this planet, and so using that, we're able to do some simulation of the radio emission that we should be able to see, that will then put constraints on when we should observe this radio emission. So, well, let's see in a few months, a year, I don't know. Well, yeah, that's just to say that if you are interested in exo radio emission detection, you can talk to Philippe Zarka, who built the instruments, because he won an ERC Advanced Grant 1 year ago, and so he's looking to hire some postdocs on that. And of course, we are also doing some SETI observations. So all the observations that are recorded are then looked by one huge pipeline that are trying to find some signal from ET. So I'm coming to the end. How to get involved? So if you want to be involved in NENUFAR, you have several options. You can contact directly the Comité Scientifique of NENUFAR, which is at this address, to join a KP, to propose a new KP for K project, sorry, to join a K project, propose a new one. If you want to be on the NENUFAR news list, to be able to join the next conference we'll have, if you want to follow the construction and the project of meeting, or for any questions. Since the call for observation, not directly from the KP, is now open, you can also propose new targets of observation. The next call will be next year, so probably springtime. So if you want to have more news on that, please contact this to be added to the NENUFAR news list. If you want to visit the website, this is the address. So it's written in French, but of course you have English option. So please go to this website if you want more information on NENUFAR. And so what are the lessons NENUFAR are giving us because it's a SCA pathfinder, sorry. So with NENUFAR, it's clear that it's better than with LOFAR, that the sky is really clean above 50 megahertz. Below that, you have a lot of ionosphere perturbations, so the sky is not clean. But above that frequency, it's really clean. So the problem was that with a huge instrument like that, you need huge power. You have power constraint. You have electronic is critical. And so with NENUFAR, we have good news on that. Well, I think the rest is okay. So we have, of course, we have the NENUFAR package on GitHub, which is open, and that will probably be useful to process the SCA data too. And then, of course, NENUFAR and SCA won't be observing at the exact same frequencies. SCA will be observing at higher frequency, so there is a nice complementarity between the two that we could have in the coming few decades, and also because it's in two different hemispheres. So that's my conclusion slide. So NENUFAR in a nutshell, it's a giant low frequency station of the LOFAR or array. It's a standalone instrument that can be, so it can be used separately from LOFAR or with LOFAR. The frequency band is 10 to 85 megahertz. We have right now 80 mini arrays constructed and 16 needs to be built. And there is a great variety of science cases that we can study with NENUFAR, from the pulsars, the planets, radio transient, the cosmic dawn, or planetary light. Thanks. Hey.
You want me to start?
Oh, let's go.
Sorry.
It was recorded, I think so.
Can y'all use your microphone, please? Thank you.
Okay. So you said on the SETI stuff, it sounds like it just runs as a piggyback thing. Are there any dedicated observations with SETI of super Earths or something like that?
Yeah, I think that they are probably really interested that if we are detecting some radio emission coming from exoplanet and star interaction, it means that there is a magnetic field that is protecting the planet. So I think once we have detected that, probably they will do some specific observation from that. But right now, I think, so because it's a KP, they were asking for some specific observation, that since they can use every observation that we are doing, they were not asking for that many time observation, because well, they can use whatever we want. So.
I have a question about the V799 TOW, the planet. Like, do you know how this one was detected? There.
Yeah.
I think that was the next.
Yeah, this one.
Never heard of that one.
I know it, but I don't remember. I think it was detected by occultation. So it was coming in front of the star, and then the brightness of the star was decreasing, and then we detect that like this, and so we were able to put they were able to put some constraint on that.
Okay. Yeah.
Yeah, that was So Tau Buddhis, it's the Turner et al. Paper from last year, and so they were looking at this stellar system because they think it's really promising because we know a lot on the orbit of this planet, and so they are not claiming that they are detecting a signal, but they are claiming that it's really possible that they detect something. Actually, if you are looking at the literature, you have, I don't know, maybe 20 papers that are claiming that they have probably detect something, but until now it's not clear. We have no clear signal. We'll see maybe. So Jack Turner, so because they were looking at this at Tau Buddhis, and they were seeing some modification in the signal they were observing, and there is some information saying that probably there is modification in the magnetic field of the star itself, and so depending on the configuration of the magnetic field, sometimes you can have reconnection with the exoplanets, sometimes you don't, and so you need to observe on the right window of observation, and so they try to do another observation when they thought based on simulation that should be a good timing to observe, and they detect nothing. So that's why they are not 100% sure that they detect something. But I think the case of the Proxima Centauri B is really promising too. They made a lot of observation, and it looks like, well, they detect something. The main problem is to be sure that it's a regular signal coming from the interaction between the exoplanet and the star, or just coming from the star. And that's the tricky part. And so you need to observe that in different configuration to see if you see some difference on the signal you are observing. And if so, well, it could be the exoplanets. If not, that's the star. So. Yes?
The 85, oh. Okay. Is the 10 to 85 megahertz band the entire frequency range that a ground-based radio telescope could?
No. Well, let me go back to, that was probably at the beginning of it. How was it? Here. Yeah, no, so here you have the opacity of the atmosphere. You can see that we are able to observe from a few centimeters up to decameter wavelength. So
okay.
depending on the signal you want to see, you won't be using the same antenna.
Okay.
And so, for example, with the HB8, so high frequency band antenna of LOFAR, you are able to observe up to 200. Yeah, I have the information somewhere, but yeah, 250 megahertz.
I saw that.
So with NENUFAR, we are only observing from 10 megahertz, or maybe 5, depending on the ionosphere condition, up to 85. That was the choice because of the design of the antenna.
Okay.
So we could have observed a bigger, but then you have LOFAR observing also on the higher frequency. So.
How do you focus?
Can you use the mic?
How do you focus the antenna?
Sorry?
How do you focus?
So it's an electronical beam.
And do you focus all the antennas or just the
Mini arrays.
Okay.
Yeah. It's the mini arrays that are focused in the beam electronically, and then you have the beam focusing one side of the sky. Then of course you have the main lobe and you have the secondary lobes, and then you have to process that to be sure that you have not sources polluting the observation in the secondary lobes, stuff like that. But
so with respect to that, it looked like you weren't quite resolving Jupiter or things like that. You're more like a degree on the sky or something. But with the DLBA or something ability of this, can you resolve say the north and south pole of Jupiter with this array?
no, I don't think so. No, because the field of view is still a few degrees. So,
okay.
Well, for example, for the cosmic dawn, I think they went down to 21 degrees on the sky. So we can't. With Jupiter, it's not a problem because I mean it's the strongest signal we have. So when we are if the sun is here, it's annoying, but during night that's only that strong signal that we have. But yeah, if we wanted to look at only one pole, no, we can't do that with any far resolution.
Even with those remote stations that you haven't hooked up yet, or
no, what you can do is that because we have the polarization, and so we know that for northern emission and southern emission, the polarization of the wave we are observing is not the same.
I just wanted to see an image.
Yeah, well, I don't have here, but yeah, if you are, so for example, with the LOFAR station, we made an observation with the Irish station, the French station, and one of the German station. And so we're using all these different stations, then by doing interferometry, which is not easy to do, we are able to locate exactly the source location. So with only 3 stations, you are making some triangularization, but it could be better if you have more stations than that. But already with 3, you can point the sources exactly where they are. which is interesting for I/O because, well, we don't know exactly the position because it's embedded in a torus. So if you want to have the exact position of the active flux tube, well, then you need to have UV images, for example. But what can you do if you have no images at that time? Well, by doing interferometry, then you can figure exactly the point, determine exactly the point of the sources. But you can't do that with only one station. Not that it's already far from a few kilometers from the distant mini array, but you need to have a baseline like a few hundred or thousands of kilometers. Is there any online questions? No.
I have a question about the, I have a microphone. The set of different radio observatories that you showed, like, are they all covering the exact same spectral, like?
Which one are you talking about? Sorry.
Like the set, yeah, the LOFAR. Are they all covering the exact same band, or there's some?
For the LOFAR station?
Yeah.
You mean all the different stations are covering the same? Yeah, they are. Actually, for the LOFAR station, all the instruments are the same. So you have HBA for high frequency band and low frequency band, but then all the instruments all over Europe are exactly the same. You can't, well, that's why with NENUFAR, they had to develop their own antennas, put them, and then ask the authorization to be connected to LOFAR, which is still in progress. That's why it's not that easy, because since it's not the exact same antenna, then the pipeline to process data and to merge all the data is different. And so, yeah, no, it was easier for the LOFAR station to have the same design, because then you know what you are doing with your signal, and what you are receiving at least. What you are doing is something else, but
okay. Okay. Is there any last questions online, or Rob? You should have. Okay. Well, thank you again, Corentin.